In this video, I'm going to be working through difference quotient. This is a skill that is contained in the 1.3 lesson and assignment. I just wanted to do a whole separate video on it because it's something that students tend to need to see a little bit more of. So what we're going to do today is understand the theory of an abstracted rate of change of a function, and then we're going to compute a difference quotient for a given function. So suppose we wanted to find the rate of change of this function from x equals 1 to x equals 4. I would identify my coordinate pairs, and what I could do is sort of think of the line between these things as model of a rate of change. So I'll give you kind of the second to do the number crunching yourself, but what I'm really asking for is the change of f of 1 and f of 4 divided by the change of 1 and 4. This is our slope formula. And so if I think about the line between these, what I'm really doing here is I'm finding a line between those 2 points in particular. Okay, think of the slope of negative 1/3, right, as the rise over run of the line running through those 2 points. If you think about it, the function isn't actually even really doing anything here. I'm really just computing the slope between 2 points. So now let's suppose instead we took some abstract x and x plus h. So let's suppose I set, where's my pen? Suppose I set this point here to be my x. So this is x. And then this point here is going to be x plus h. That means that h is the distance between these 2 points. And I want to find the rate of change of this interval. Well, I'm going to compute the rate of change formula. I'm going to use the slope formula that I've done before. So that's f of x plus h minus f of x divided by x plus h minus x. These x's are going to cancel, which is kind of nice. And I end up with this formula here. Right, now what does this even mean? Well, what we're really doing here is I'm finding the slope of the line. Oof, that's not even close. Sorry about that. Let me try that again. Finding the slope of the line passing through these 2 points. This number m is what I'm going to get for this value. Okay. Now, it might help to actually see kind of what we're looking at here. So let me show you. So I'm going to set up a new screen share, figuring this technology out as well. So let's suppose I've got this function here. And let's say I'm going to talk about this coordinate pair, the one to the left. Let's take that value and set that equal to, let's just go ahead and not worry about our h value for right now. We'll get there. Let's set a coordinate point at x equals 1. Why not? And now let's set the h value, that's going to be the distance on the x-axis between the 2 points, to be 3. So that means that now we're looking at this value here with an x value of 4. Right here, we said the x value was 1 before. I moved 3 units over. That's great. And now what this line, the red line, is showing here is the rate of change between those 2 coordinate pairs. And here I see the m value is equal to negative 1. Right? The slope between these 2 points is negative 1. As I start to take this h value and I start to mess with it, I see that I'm changing the rate of change between these 2 coordinate points, which makes sense because I'm changing where the points are. Now, as I take that h value and make it really, really close to 0, what I'm doing is getting closer and closer to finding the rate of change at the exact point. Now, when h is 0.1, I'm really close. But when I make it 0, I've got a problem. I'm undefined because now I'm saying h is 0. Well, I can't divide by 0. Okay. So that's really what we're doing here. Let's go back to our presentation. Boop. So let's actually compute a difference quotient here. So this is the difference quotient formula. I'll tell you that this will not always be given to you on tests or anything to that effect. So have this memorized as your difference quotient. It's not kind of a crazy thing if you think about it, like you've got a difference and a quotient. So that's what the formula is. You have to remember the x plus h. So what I'm going to do first is compute the composition. That's going to be f of x plus h. So when I'm talking about a composition, what I'm talking about is a function inside of a function. So if I think about just the function f, before I plug anything into it, it's 2 times the input minus 3, right? Here we see 2x minus 3. It's 2 times whatever the input is minus 3. Now what I'm saying is the input is going to be x plus h. All right, so now what I'm going to do is distribute the 2. So I get 2x plus 2h. Goodness gracious. Minus 3. All right, now I've got my composition. So now what I'm going to do is plug this into the formula. Okay, so that's this part here. And then I subtract the original function and I divide it by h. Now the original function is that 2x minus 3. So actually just go ahead and take the negative and distribute it through here. And now what I end up with is 2x plus 2h. This time I didn't forget the 2. Minus 2x plus 3 all over h. All right, well, just by looking at this, I see that there's a lot of really nice canceling. The 2x's are going to cancel. That's pretty cool. The 3's are going to cancel. And now I end up with just 2h over h. And now the h's cancel, and I'm left with just 2. Okay. Now, this actually makes a ton of sense if we think about it. This is a linear function, right? So if I think about a linear function, it's got a y-intercept of -3, and it's got a slope of 2. So what that means is, if I choose any 2 points, the slope between these 2 points is going to be 2. That's the slope. It makes perfect sense. The slope is always going to be 2, right? Because it's a linear function. Now, if that's not terribly obvious, that's okay. This formula would do that for us. Okay. So this is what a difference quotient is. This is how we compute a difference quotient. As a note, this step here, there should always be an h cancellation. H should always cancel. If h doesn't cancel, there's something you're probably missing, or calculus is false, and calculus is not false. So there's something you're missing. Okay. Now, take a second, try and do this one on your own. As a note, you're going to have to do a lot of variable pushing, a lot of number crunching here, but take the time, try it on your own. Okay, so first, you're going to notice that I'm asking you just to do the composition first. That's cool. So first, I'm going to start with everywhere I see an x in this function, I'm going to put an x plus h in its place. Now, as a note, I'm going to address this part here first. Something you need to remember. A plus b squared is absolutely not just a squared plus b squared. You don't just distribute the square. That is not true. Okay? That's absolutely not true. What you're going to need to do here is actually use FOIL. Okay? And then don't forget your -2. We'll just go ahead and put that out there. So now we're going to use FOIL. So we get -2, and then x times x is x squared plus xh plus hx plus h squared. And then why not? We'll go ahead and distribute this. Now, these collect up because they are the same. And now I distribute. Now from here, you're gonna think to yourself like, oh, now there's cancellation. No, there's not, because we were only asked for the composition. So that's what we end up with here. That's this answer. All right, now we are so far from done when it comes to, well, we're not really that far from being done, but we still have a little bit of work to do if we want to compute the actual difference quotient, which is what we're doing in the second part of the problem. Truthfully, I mean, if we didn't even do the first part of the problem, we would have had to have done it anyway. But what you're doing is you're going to take that result from the first part of the problem, and you're going to use that here in your formula. So let's just go ahead and sort of copy paste that in. Remember, if we're doing this correctly, there's going to have to be some h cancellation at the very end. But we don't know if that's going to happen yet. So here's to hope. All right, now, this is my original function. So what I'm going to go ahead and do here is distribute the negative. So now be very careful with my signs. Really take your time on this. It is such a bummer when you get down to the bottom and you realize that something isn't canceling, or like if it is canceling, it's only canceling because you're doing something illegal anyway. All right, now we look for the stuff that we can knock out. Simplify is really important here. All right, so these right here, these are going to knock out. That's great. Let's see. Oh, these right here are also going to knock out. That's great. Let's see. Oh, and these are going to knock out. And so now I'm left with and here's something that's really nice. I can factor out an h. Technically, I could have also factored out a 2, but ultimately, I'm just trying to cancel the h anyway, right? So now these cancel. And what I end up with is this result here. And we are done. That is a difference quotient. So I showed you two examples, one with a linear and one with a quadratic function. Make sure that you're taking your time and using FOIL. You're not just distributing squares. That's going to be where students make the most mistakes. Also, make sure that you really take the time to be sure that things are actually canceling in legal ways, so that you aren't just kind of fudging the answer at the end. That becomes pretty obvious when I'm going through tests and homework and all that jazz.